Alrighty, good afternoon, everybody. Give me just 1 second to get a little bit organized here. I have a class that ends immediately before your start, right at 2 o'clock. It's always a little bit of a struggle for me to change gear. But that'll work. We'll give folks just a second to drift in, and then we'll jump over and get started. Let me get this set up. And transformations. All right. What's this? You guys can't see my emails. Keep on going. Okay. So here we go. This is pre-calc section 4, and today is the 9th. So last week we talked about a bunch of stuff. We talked about rates of change, increasing, decreasing mins, maxes. We solved some inequalities using graphs, some equations using graphs. It's all good shit. This week, we're gonna change tack again. So today, it's still going to have to do with graphs, but less about trying to answer particular questions about a given function or solve an inequality or solve an equation, and more about just drawing graphs. So we're going to talk about transformations of graphs. This is a hugely important topic because you take a family of functions that you know pretty well, we'll call them parent functions, and you'll be able to get all sorts of other graphs from those by dragging them left, right, up, down, flipping them over, stretching them out, doing whatever. We're going to have 4 kind of fundamental transformations and then several special cases of each of those. And then if there's time, what's the other topic? If there's time, we'll start to talk about combining functions. But first, definitely transformations. If you need more time on last week's material, on any of that homework, or if you want to talk in more detail about those problems, you should reach out to me. For more time on the homework itself, submit an extension request in WebAssign. I'm going through several times a day and clearing those out. But more time is only helpful if you're doing something productive with that time. So make sure if those problems have not been solved already and are not coming to you readily, that you come to me for help. Remember, you can also always go to the tutors in the Learning Commons for help. You can access them by following the links that I've put on our Canvas page. So if you go to our page here in Canvas, go to the home. There is a link here that'll guide you to the tutors. Just follow the instructions. So you'll go to Math and Statistics, and then that'll take you to their Canvas page, and you'll click on a link to get into a waiting room for a tutor. Today we're going to talk about transformations of graphs. So the fundamental transformations, and what section is this? Sorry, this is section 2.6. The basic idea is this. You'll start with some parent function, and then you'll apply a sequence of transformations to that parent function to get the graph of a desired function. So maybe I ask you to graph the graph of the function f of x from the graph of a parent function g of x. And your goal is to recognize f as a transformed version of g. The transformations are as follows. If f of x is like the square root of x minus 5 or x minus 3 all squared, if you've subtracted a number on the inside, that will be a horizontal shift. The word to obtain. Obtain, O-B-T-A-I-N. So this is a horizontal shift. There's also a vertical shift. If you want to graph x squared plus 5 or the square root of x minus 7, those will come as vertical shifts. I'll explain left, right, up, down. It's a little bit subtle and it's going to depend on which of the guys we're looking at. So for now, follow along with me and trust that I'll come back and I won't leave you hanging there. The other two forms of transformations are scalings. If I multiply on the inside of your function by a number, that will be a horizontal scaling. And if I multiply on the outside by a number, that would be a vertical scaling. Left, right, up, down stuff. So here, if C is a positive number, you will move to the right. And if C is a negative number, you'll move to the left. There's a minus kind of built into the formula. Here, if C is positive, you'll move up. And if C is negative, you'll move down. Here, if C is bigger than 1, then you will be compressing. And if C is larger than 1, if C is bigger than 1, you'll be compressing. And if C is smaller than 1, you'll be stretching. Here, if C is bigger than 1, you will be stretching, and if it is smaller than 1, you will be compressing. So we go left, so we'll go right if C is positive, and left if C is negative. Here you'll go up if C is positive, and down if C is negative. Here, you will be compressed if C is bigger than 1, and you'll be stretched if C is less than 1. And here, you will be stretched if C is bigger than 1 and compressed if C is less than 1. So what you'll notice is that kind of the rules, scaling is stretching or shrinking, right? Rather than sliding around, you can scale things. Like you stretch everybody out by a factor of 2 vertically, that would be a vertical scaling. That would be a vertical stretch, right? So scaling is where you stretch or shrink everything. Special cases of scalings are reflections. So here you will flip horizontally if C is negative, and here you will flip vertically if C is negative. So 2 special cases of scalings are flips. and a scaling is a stretch or a compression. We use the word scaling because that's the word for making something larger or smaller. You scale it up or you scale it down, like a 1/10 scale model is 1/10 of the size of the original in every dimension. By far, the best way to get your hands or get your head around this is to practice with examples. A word of warning, the horizontal things kind of work the opposite way of what your intuition would want them to. So for our first example, let's graph f of x, which is x minus 3 all squared, as a transformation of the parent function g of x equals x squared. Here, f of x is g of x minus 3. So what sort of transformation do I need to apply to the x squared graph to get this guy? Which one of these four things does this look like? Yeah, it's a horizontal shift. Looks like this, right? Here, C is positive because there's a minus sign built into the formula. X minus 3, G of X minus C, G of X minus 3. Oh, so C is 3. So we're going to go to the right by 3 units. So here's the graph of the original, the graph of G. G of X is just X squared. We should always track a few points. So I'll track 1, 1, negative 1, 1, and 0, 0. This is the graph of my original, my parent function. And then if I transform that by sliding everything to the right by 3 units, I'll get the graph I want. Zero, 0, if I shift it to the right by 3 units, becomes 3, 0. Negative 1, 1, if I take this point and I shift it to the right 3 units, it'll become 2, 1. And 1, 1, if I shift him to the right by 3 units, it'll become 4, 1. So this is the graph of x minus 3 all squared. Good shit, right? Not too hard. We can see what it looks like to do more than one of these at a time. Here again, my parent function is just x squared. So f of x is, how do I get this from this? That's g of x plus 2 minus 1. So what's going on here? I've got a horizontal shift of some sort because I'm adding or subtracting on the inside. And I've got a vertical shift of some sort because I'm adding or subtracting on the outside. So f of x is the graph of g of x. We've got two shifts here. It shifted left by 2. Not right, but left. Because remember in the formula, the recipe for these shifts, x minus c. Well, here I've got x plus 2. That's the same as x minus negative 2. So we're going to get shifted left 2 units. And then this guy tells me we're going down 1 unit. So to get the graph of x plus 2 quantity squared minus 1, I start with the graph of x squared. And I'll shift left by 2 units and then down by 1 unit. So here's the shift left by 2 units. And again, we should track some points. 1, 1, 0, 0, and maybe negative 1, 1. 0, 0 will go to negative 2, 0. 1, 1 will go to negative 1, 1. And negative 1, 1 is going to go to negative 3, 1. That's the left shift. And then one more, we have to go down by 1. Left 2 and down 1. So I take that graph, this graph, and I finish by moving him down 1 unit. So negative 2, 0, that vertex is going to come down to negative 2, negative 1. Negative 3, 1 is going to come down to negative 3, 0. And negative 1, 1 is going to come down to negative 1, 0, like this. So the question we're asking is, what do I need to do to this? Or what do I need to do to x squared in order to get this? Adding 2 on the inside tells me to go left 2 units. It's a horizontal shift because I'm adding or subtracting something on the inside. And I go left because it's a minus and negative. There's a negative built into the formula for horizontal shifts. So if you've got g of x minus c, that'll always be a horizontal shift. If c is positive, like x minus 2 or x minus 5, then you're going to the right. If c is negative, like g of x minus -2 or x minus -5, then you're going to the left. But nobody writes minus -2 or minus -5, they write plus instead. So this g of x plus 2, I'm thinking of that as g of x minus -2. So I'm going to the left. Easy way to think about it, adding on the inside takes you left, subtracting on the inside takes you right. So adding 2 on the inside takes me left 2 units. That goes from here to here. And then subtracting 1 on the outside brings me down by 1 unit. So here's the left shift, and then here's the shift down. And this is my final answer. This is my graph. So when you add or subtract stuff on the inside, that moves you left or right. When you add or subtract stuff on the outside, that moves you up or down. If you add on the inside, that takes you left. If you subtract on the inside, that takes you right. If you add on the outside, that takes you up. If you subtract on the outside, that brings you down. So this says take the graph of x squared, move it left 2 and down 1. And that's exactly what I did here. I took the graph of x squared, I moved it left 2 and then down 1. Is that making sense? Okay. Let's play with 1 or 2 more examples and see if it helps. Let's make this an abstract example. Oh no, probably better to keep it concrete. So let's start the graph like this. We'll call this x cubed. Shouldn't really be going completely vertical there, but g of x is x cubed. If I wanted to drag this to the right by 1 unit, what would f of x be?
X cubed minus 1.
So if I did x cubed minus 1, if I subtract 1 on the outside, that would bring me down. If I want to go to the right, then I need to subtract 1 on the inside. Yeah, Austin's got it there. This would be x minus 1 cubed. Because that is g of x minus 1. All right, so subtracting 1 on the inside brings me to the right by 1 unit. I can go back to the previous page just for 1 second, sure. Yeah, these are the last example we did there. Okay. It's going to take some time. This isn't a simple thing, right? So this is a tricky subject, and it's going to take some time to wrap your head all the way around it. One of the ways to think about this is to ask yourself what inputs lead to what outputs. So for example, on the graph of x cubed, I know if I plug in 0 for x, I'll get 0 out, right? G of 0 is 0. Here we had this graph, and I wanted to figure out what the algebra would look like to transform this to this. I know that the output 0 here comes from the input 1. So how would I have to change the algebra of this function to make the output equal to 0 when the input is equal to 1? Well, I have to subtract 1 from all the inputs, right? This guy, if you plug in x equals 1, now you'd have 1 minus 1 cubed. Oh, that is 0. Let's try a scaling next, and we'll run through some scalings and then see if we can come back to the shifts with a little more clarity. So another example. How would I get the graph of f of x equals 1/2 x squared from the graph of just good old-fashioned x squared? So here, if you plug any input into G, the output will just be that number times itself. If you plug any input into F, the output will be that number times itself, then times 1/2. So if you make a table of values for each of these, g of x is just x squared. Well, -2 squared, that's 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. If I do the same thing for f of x, what's the relationship? Well, if I plug in -2, then I'd have 4 times 1/2, that's 2. If I plug in -1, I'd have 1 times 1/2, that's 1/2. If I plug in 0, I'll still get 0. If I plug in 1, I'll get 1/2 times 1 is 1/2. If I plug in 2, I'll get 1/2 times 4, which is 2. So let's compare the graphs. We'll even draw them on the same coordinate axes. So here's 1, 2, -1, -2, 1, 1, 1. So g of x I'll do in purple. -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. Here's the graph of g. This is my parent function. The graph of f has -2, 2, 1, 1/2, 0, 0, 1, 1/2, and 2, 2. So what's the relationship between the blue and the purple? F of x here is the blue. The blue has been smooshed down vertically. Can everybody see that? The blue guy, this guy, has been smooshed down vertically from the purple guy. You take the purple guy and you go, and you get the blue guy. That's because this guy has been scaled by a factor of 1/2. The is a vertical thing. This is a vertical scaling. In other words, we've multiplied all the y values by 1/2. Take all these y values and multiply them by 1/2 to get these y values. Well, of course, because f of x is 1/2 times g of x, 1/2 x squared and x squared. So this is a vertical scaling. here by the factor of 1/2. And that's the end of this blue pen. So I hope this is starting to crystallize. It will take time. For the next few examples, I'm going to flip over to Desmos. And you don't have to draw, you don't, sketch whatever you feel like sketching, but mostly I want you to just think along with me. Okay, so it's all right if this feels a little bit difficult at first, but come over here and think along with me. Fresh graph. So let's start with some parent function like x squared. I'm going to build some other functions out of this. I could make this g of x minus 2. And you see that that shifted everything to the right by 2. Right? To get the blue from the red, you shift everything to the right by 2. If instead of adding or subtracting 2 on the inside, I added 2 on the inside, that will bring me everything to the left by 2. So the red guy is the parent function, he stays where he is. And the blue guy is my transformed guy. If I add 2 on the inside, that brings me to the left. If I subtract 2 on the inside, that brings me to the right. So X stuff is horizontal stuff, is stuff that happens on the inside of the function. Y stuff is vertical stuff, and that happens on the outside of the function. Okay, so what else could we do? If I add 1 on the outside, that will bring everything up by 1 unit. Because I'm adding 1 to all the y values on the graph. If I subtract 1 on the outside, that will bring everything down by 1 unit, because I'm subtracting 1 from all the y values on the graph. And you can start combining these sort of things. We could do something like this, where you come to the right by 2 units and then down by 1 unit. So yeah, what Allison said is correct. Horizontal affects the x values, and conversely, playing around with x stuff or inside stuff affects the graph horizontally. And y stuff, if you play around on the outside of the function, that will come from messing around with y values. Okay. What the hell? Here's the graph of 1 over x squared. Suppose I wanted to know, what does the graph of 1 over x minus 2 squared look like? Do you see the algebra relationship between these two things? To get this from this, the difference in the formulas here is that I've subtracted 2 on the inside. So I would expect this to look the same as this with what shift applied? And there it is. If you take the red and you drag it to the right by 2 units, you'll get the blue. What about now? Yeah, exactly. I'm subtracting 5 on the outside of the function. It's not 1 over x minus 5 squared. It's 1 over x squared minus 5. So this would be a shift down by 5 units, and there it is. Every point here gets moved down 5 points, 5 units. Every point gets moved straight down by 5 units. Okay. What about here? So I've changed this one more time. We're not looking at the graph yet. We just have the graph of the original, the parent. What transformations have been applied here? Yeah, good. The x plus 3 on the inside tells me I'm moving left 3 units, and the plus 2 on the outside tells me I'm going up 2 units. There it is. This whole red graph has been moved left 3 and then up 2. A few days ago, a few weeks ago, we would have no idea what this graph looks like, and we would have no idea how to get it. But the basic idea is that now, as long as you have a decent library of parent functions, you can come up with lots of other shit by recognizing them as transformations. And what Lily said in the chat there is correct. So the plus 2 on this outside says add 2 to all the y values. The plus 3 on the inside says shift everything to the left by 3, or equivalently, subtract 3 from all the x values. Okay. Let's come back out of Desmos. And do one more practice problem like this by hand, and then we're going to talk about scalings. And then we're going to add something here. We're going to find the domain and range. So if I want to graph this function using transformations, first I need to identify a parent function, a graph whose shape is basically the same that I can move around in order to get this guy. Who is my parent function here? Square root of x, right? This looks like a transformed version of root x because we've done some shit on the inside, we've done some shit on the outside, but the fundamental thing here is the square root operation. So I begin with g of x equals the square root of x. What does that look like? Well, that looks like this. All right, it's like half of this sideways parabola. You've got the point 1, 1. Far enough out here, you've got the point 4, 2. You've got the point 0, 0. All right, this is what the square root function looks like. What transformations should I apply to this graph in order to get this graph? Good. So my next graph, this guy tells me to shift right by 2 units. And this guy tells me to shift up by 1 unit. I'll do one at a time. If I shift right by 2 units, my graph will look like this. And we track all 3 of those points through each transformation. So 0, 0 will go to 2, 0, because I'm moving it to the right 2 units. 1, 1 will go to 3, 1, because I'm moving it to the right by 2 units. And 4, 2, he will go to 6, 2, because I'm moving him to the right by 4 units. And this would be the graph y equals the square root of x minus 2. That's just having done the right shift. And now my last move would be to bump everything up by 1. So 2, 0 is going to come up to 2, 1. 3, 1 is going to come up to 3, 2. And 6, 2 is going to go up to 6, 3. And the final result there will look something like this. So we have 2, 1, 3, 2, 6, 3. And this is f of x. So this is my sequence of graph, my sequence of transformations. Here's the parent. I move it to the right 2 units, and then I move that up 1 unit. The domain and range game here is interesting. The domain of the original is 0 to infinity, closed on the left, open on the right. And so is his range. Because if you smush this down onto the x-axis, 0 gets hit, and so does everybody to the right. If you smush this over onto the y-axis, 0 gets hit, and so does everybody above. The domain of my first transformed function, well, now if I smush this down onto the x-axis, 0 doesn't get hit, 1/2 doesn't get hit, 1 doesn't get hit, 3/2 doesn't get hit. The first thing that gets hit is 2. And the range here is still 0 to infinity. Because if you were to smush this onto the y-axis, the range, all the y values, hasn't changed. And then in my last version, my domain is still, if I smush this down onto the x-axis, my domain is still 2 to infinity. And this time it's my range that's changed. I bump everything up by 1. So the smallest y value in my range is no longer 0, it's now 1. Looks like this. So this is how we would graph that guy using transformations. Start with the parent function, apply those transformations one at a time until you get to your final function. You always want to track a few points along the way. And the rule that I have in this class is that you guys need to track at least 3 points through that whole process. All right, that's what you'll always see me doing. And that's what I expect you guys to do as you solve your homework problems and on tests. Questions about each of these transformations or how we end up at this final graph? Okay. So then it's time for us to start talking about some scalings. And to do that, I want to go back to Desmos and play around a little bit. So come back over here with me. And let's start with everybody's favorite function, just good old-fashioned x squared. If I wanted to shrink this graph, I could multiply on the outside by a number smaller than 1. We looked at that, right? Like y equals 1/2. Oh, not 1 over x. 1/2 x squared. See how the green is a vertically smushed down version of the red? If I wanted to make it taller, I could multiply by something bigger than 1. Multiply all the y values by 2, and that'll make the green taller. I haven't shifted. Notice that they're both still going through the origin down here. I've just stretched. If I wanted to make it much taller, then I could multiply by a bigger number. If I want to make it very, very, very small, then I could multiply by a number much, much smaller than 1. The fun comes when you start playing around with the sign of these scaling factors. If I multiply all the y values on the red graph by -1, that has the effect of flipping them over the y-axis, flipping them over the x-axis, doing a vertical flip. And if I wanted to also stretch it out, I could do that. Or if I wanted to also make it small, I could do that too. So the vertical scalings, well, there are no asymptotes here. And in general, scalings won't alter vertical asymptotes, but they alter the size, right? It's like a stretch or a compression. Think of those funhouse mirrors. Everybody, I don't know. Even I didn't really see many of those in like circuses or whatever as kids, but I know what they are. Those funhouse mirrors that make you look like tall and skinny or short and fat. The number that you multiply by out front says how much taller and skinnier or how much shorter and fatter you get. So if I multiply by a number that's really big, like 5 or 10 or 20, that'll make this thing much, much taller and much, much skinnier. If I multiply by a number close to 0, like 1/10 or 1/5 or 1/2, that'll make it shorter and fatter. Right? Shorter and fatter. Taller and skinnier. The fun comes when you start trying to combine these things. So I'm going to give us a transformed function. And I don't even want to worry about graphing it at first. I just want to worry about identifying the transformations. So identify the parent function and transformations. Okay, can everybody see this? So first things first, what's the parent function here?
X squared.
Good. Now, what sort of transformations must one apply to this in order to get this? Let's start with the stuff that we've been doing. What does adding 3 on the inside do? Good, this is a shift left by 3. And this is a shift up by 4. What about this? There is a flip because the number we're multiplying on the outside by here is negative. And also a vertical compression. Yeah, we're squishing down, which will also make it look fatter. A vertical compression and a horizontal stretch can look very similar. So this is a vertical flip and compression by 1/2. Here's the place where this stuff gets challenging. You have to choose the order. Should I do the shift left 3 and then up 4 and then flip and then compress? Or should I compress, flip, shift, and then shift? Does it matter? The answer is yes, it does matter. And you can kind of think about it as an order of operations thing. But here's my advice. Always apply horizontal transformations first. So horizontal transformations before vertical. And within each of those categories, do scalings before shifts. So scalings are stretchings, compressions, or flips. So the order here would be shift left by 3, then do the vertical flip and compression, then shift up by 4. So you take care of all the horizontal stuff before doing any vertical stuff. So first I would look, are there any horizontal scalings? And there are not. Then I'd go, are there any horizontal shifts? There are. Then I would go, are there any vertical scalings? And then I would ask, are there any vertical shifts? And to answer your question, Lily, it is. It's the same thing as following the order of operations. If you look on the inside here, if you wanted to find f of some number, the first thing you would do is add 3 to that number. So that's you doing the shift, the horizontal shift first. If there was a horizontal compression, that would come from a number multiplying the x here, and you would have to do that before the shift. Then you would square, which is kind of giving you the shape. Then you would do the vertical compression and the flip. And then finally you would do the vertical shift. But this is the rule that works for most people. So you'll apply these first any horizontal scalings, then any horizontal shifts, then any vertical scalings, then any vertical shifts. That's the order. Within each category, do scalings before shifts. So the order is first, any horizontal scalings. Second, any horizontal shift. Third, any vertical scalings. And then last, fourth, any vertical shifts. So that's the rule. Let's see if we can do that for this function. I'm going to start with x squared. So I know we're still writing. That's my parent function. And I'm going to track those same 3 points because they're nice, easy points to track. -1, 1, 1, 1, and 0, 0. And then my very first transformation, since I don't have any horizontal scalings, but I do have a horizontal shift, first thing I should do to this to get this is the horizontal shift. So I'll go ahead and shift everything left by 3 units. So the point 0, 0 is going to go to -3, 0. The point 1, 1 is going to go to -2, 1. And the point -1, 1 is going to go to -4, 1. This is the graph y equals x plus 3 quantity squared. Now that there's no more horizontal stuff to do, I'll do the vertical scalings. Right? I'm at this step now. The vertical scaling here is a compression by 1/2 and a flip. So the next graph I'm going to draw -3, 0 will stay there. He's going to be shorter and fatter and flipped over. So something like this. -4, 1 is going to go to -4, -1/2. His height is cut in half and he is flipped over. So he's flipped and compressed. -2, 1 is going to go to -2, -1/2. So here is the graph y equals -1/2 times x plus 3 quantity squared. And then my last move is to bump everything up by 4. So the point -3, 0 is going to go up to -3, 4. The point -4, -1/2 is going to go, if I move him up by 4 units, I'm adding 4 to -1/2, that's 3.5. So that would be -4, 3.5. And similarly, -2, -1/2 is going to be moved up 3 to -2, 3.5. And otherwise, the shape stays the same. So this last graph down here, this is your final answer. This is the graph of f of x equals -1/2 quantity x plus 3 squared plus 4. And this is the sequence of graphs that we would draw to get there as transformations, doing them in that order. All right. And can we fit it all there? Yeah, there it is. Here's the original. We move left 3. That's our horizontal shift. Then we do our vertical scaling. That flips us over and compresses us. And then we bring everything up by 4. Right? And this would continue like this forever and ever, amen. Yeah, what Leanne said is correct. If you multiply on the outside by a negative number, by a number that's less than 0, that will flip you vertically. So the only one of these transformations we haven't dealt with explicitly yet is a horizontal scaling. And those are definitely the trickiest. So questions about any one of these steps, how I got those points that I'm tracking, how we drew the graph, any of it, before we move on to this last and most challenging piece. Sweating like a pig up here. Okay. A question I enjoy asking college algebra students. They don't like it very much though. What is this? We know that square roots don't like negative numbers. Come on, focus. How could I graph the square root of negative x? My parent here is definitely the square root function. And this transformation, what we did here is we multiplied on the inside by -1. That's a horizontal scaling. It's a particular scaling. It's a flip. So just like if you multiply on the outside by a negative, that flips you vertically. If you multiply on the inside by a negative, that flips you horizontally. So here is the original square root x function. We looked at him earlier. Goes through like 1, 1, 0, 0. And eventually he'll go through 4, 2. This is y equals square root x. If I wanted to graph the transformed version, he's just flipped over horizontally. This is y equals the square root of -x. So he'll go through -1, 1 and -4, 2. And he'll continue on like that forever and ever. So if you multiply on the inside by a negative, that is an example of a horizontal scaling. And if that negative is -1, it's just a flip. The domain here is 0 to infinity. The domain here is -infinity to 0. So everything flips over horizontally when you multiply on the inside by a negative number. Let me try to string a few of these concepts together. Let's graph, and this will be our last example for today. as it's written, I can't quite see this as a transformation. But if I force factor a 2 inside the square root to write that as 2 times x minus 1/2 in parentheses, then I can see this as a horizontal scaling, and I can see this as a horizontal shift. So what we're going to do is we're going to compress in horizontally by a factor of 2, and then we're going to shift to the right by 1/2. My parent again is the square root function. So the graph of the parent, we know looks like this, going through 1, 1, 0, 0, and 4, 2. If I compress horizontally by a factor of 2, that means I'm bringing everything in like this by a factor of 2. So my first step here is to do any horizontal scalings. If I bring this guy in by a factor of 2, that means I'm going to divide the x value by 2. So rather than 1, 1, I have the point 1/2, 1. And rather than 4, 2, I have the point 2, 2. 0, 0 stays where he is. So this is y equals the square root of 2x. And then finally, I would drag everything to the right by 1/2. So we're not quite done with class. I think I'm supposed to have you guys till 3:15. So I'll ask that you hang with me for a second here. If I now shift everything to the right by 1/2, 0, 0 will go to 1/2, 0. 1/2, 1, I'm shifting to the right by 1/2, he will go to 1, 1. And if I shift 4, 2 to the right by 1/2, he will go to 4.5, 2. I'll call this 4.5, it's 2. This guy is 1, 1. So here's your final graph. This is y equals the square root of 2 times x minus 1/2, which is our function. So what you want to get good at, being given an expression like this, find a way to read off the transformations and the parent function. Then you draw the parent function and one at a time apply the transformations.
I have a quick question.
Terribly hard, but it will take a lot of practice. Yeah, sure, go ahead.
For like the last point on the third graph, wouldn't it be 2.5?
Oh, what did I do? Yeah. Sorry, 2.5. 2.5.
Okay, cool. Thanks. Sorry.
Yes. Yeah, no, you're good. You're absolutely correct. We're driving everything to the right by 1/2. So this guy goes to 1/2 plus 1, 1, which is 1, 1, and this should be 2.5, 2. Yeah, very good catch. Thank you. Yes. Yeah, perfect. Thanks. Okay, so again, the thing you need to practice, looking at an expression, identify the parent function and the transformations. Then draw the graph of the parent function, and one at a time in correct order, apply the transformations. Horizontal scalings first, then horizontal shifts, then vertical scalings, then vertical shifts. That's the safe order. Next time, I'll show you some examples of transformations that don't commute, or if you do them in the wrong order, things come out wrong. And then we're also going to talk a little bit about combining functions. So there's some cool relationships between these transformations and graphs that have certain symmetries and ways you can put functions together to get other functions. But for now, this is where we're going to finish. Lily asked a good question. We haven't any quizzes yet. So this is the first section that I intend to quiz you on. Really this and the last section from last week. So I'm going to work on putting together a quiz for you guys that will be due next week. And it'll be in WebAssign. It'll be just like a short homework thing where instead of having infinite tries on the problems, you just have 1 or 2 tries on each problems. And there will be like 1 problem on increasing and decreasing, 1 problem on average rates of change, and 1 problem on transformation, something like that. But for now, don't panic. I will talk more with you about the quiz and when it will be due on Friday. Wait, sorry, shit. That sucks. You guys don't meet on Friday, do you? Boy, we really got screwed this week. Maybe I can't give you a quiz quite yet then. So for now, watch for the homework in WebAssign. All right, there will be a new homework in WebAssign. We may have to push the quiz back a little bit because we don't have another class meeting this Friday. I'll post an announcement letting you know which way I decide to go on that because we do need to have our first quiz. I want to have a quiz or 2 under your belt before the first exam. First exam is coming up. It's getting close. So after we cover transformations and one-to-one functions, we'll be ready for our first test. So there's going to be a new homework this week, maybe a quiz this week. I'll post an announcement a little bit later in the day. Right now, I got to run to a doctor's appointment, but watch the Canvas announcements for a little bit more information in the near future. Really, I'm sorry that you guys don't have a class meeting this Friday. It's a shame with the holiday that we just get down to a 1-day week. That sucks. So I may also post like a supplemental lecture video, something like that, to take place of what we missed on Monday. But for now, this is it, right? Focus on transformations, focus on drawing graphs by hands. The homework is not going to make you draw graphs by hand. It's going to ask you to pick a graph from a list of graphs. That sucks. Don't just do that. Draw them by hand, then pick. All right. I promise if you do that, it'll help on the test a lot. So draw the graphs by hand first, then pick from WebAssign. Don't just guess and check in WebAssign. Okay. Unfortunately, that's where we've got to leave it for today. But I will see you guys Monday at the latest. Hopefully I'll be able to get something together where we can interact a little bit more. Maybe just a video I'll post to Canvas. So watch Canvas. Otherwise, I'll see you guys on Monday, okay? All right. Take care, guys. I hope you have a good rest of your afternoon. And yeah, that is all.